another use case that we are looking at uh, now as we approach elimination is the the use case of importation of samples, which of course is needed for certifying malaria-free and so on. So we have been working on this issue, and uh, it's all very preliminary because we haven't got a full methodology yet. But Tess here, who's a research scientist in our team here in Bangkok, she will give you a sort of status of where we are on this use case. Tess?
Thank you, Oliver. Yeah, so as Oliver mentioned, this is work that we will execute in the coming year. But today we would like to share some considerations on how we will approach with developing methods for detected imported EF cases using genetic data. First, I will share some background on importation as a public health use case and how genetic information might be useful in addition to travel history to predict importation. And then I will give you an idea how genetic information could be used for classification by demonstrating one measure, so genetic distances that were calculated from the PF7 release. One based on the 100 SNP genetic barcode, which is currently used by GenRe-Mekong, and second by using SNPs that were derived from the whole-genome. And then I will end with a discussion and plans for our future work. So as the Eastern GMS is approaching elimination, it becomes more and more important to demonstrate that there is no local transmission in a country, and then country would qualify for malaria-free certification, which is achieved if there have been at least 3 years of no indigenous cases, and then the WHO can provide the certification. And for example, China was declared malaria-free in June of 2020, which concerns the UN as part of the GMS. So some definitions: imported malaria case is an infection that was acquired outside the area where it was diagnosed. And an indigenous case is an infection which is contracted locally without evidence of importation. This is a graph that shows any malaria case in the GMS in 2022 and 2023, and imported cases or cases that were labeled as imported. And what you can see is here that in the Eastern GMS, cases are very low, and then in China they are almost absent, and you see that virtually all samples that have been, or cases that have been confirmed, are also labeled as imported. And then in Thailand, you see that cases are increasing, predominantly in 5x. Already a big part of them are labeled as imported, and these are all spillover cases from Myanmar and subsequent local transmission. Oh, okay, this is better. So a question an NMCP public health official might ask is the malaria case that we observe at hand, is this one imported or not? And to answer this question, currently travel history interviews are conducted. The downsides from travel history are recall bias and uncertainty of infection origin. Here is one study that showed that in the US, of 265 patients with known imported malaria, only 65% reported travel history. But what I just heard when talking to Richard Mott, it really depends on the person that is taking the interview. And if you have a person that's the interviewer is trusted by the person that's interviewed, the numbers could be a lot higher. So this is only one study. So how can genetic information be of additional use to predict importation? So we start with a basis. So P. falciparum, like all organisms on planet Earth, are likely to reproduce with other not parasites for all organisms, but only PF, with other parasites that are spatially close. And thus genetics can reveal not only ancestry, but also geography. And our current research question is, what is the predictive value of genetic information when classifying the location of origin of a PF sample? So genetic information, one measure that could be used is genetic distance. A little bit of background on what genetic distance is. So it is a measure that can go from 0 to 1. And 0 means that two samples are identical, or clones, or identical twins even. And as the genetic distance goes up, the two entities are becoming more genetically different. And then one would be the upper scale or the top of the scale, but it's not, couldn't find an example when that is the case. I think it doesn't exist. So genetic distance and geographical distance, how do these two relate? On the left, you see an example of the Thailand-Myanmar border, which there are 4 healthcare units. Those are the black dots. And then the stripes, the lines are the connections between the healthcare centers, and those express genetic distance of the parasites that were collected in each of the healthcare units. And what you can see is that neighboring parasites from neighboring healthcare units, so here, for example, those are more genetically similar than the health parasites that were collected in the most upper northern healthcare center and the lowest, more southern healthcare center. So here you see the thin line going here, which indicates that they are more genetically dissimilar. And when you look at data from the malaria, one of the malaria gen releases, you see a graph here that shows genetic distance, geographical distance in kilometers, and here genetic distance on the y-axis. And what you can see is that here samples that were, for example, collected in South America and Southeast Asia were most geographically separated from each other, as well as most genetically dissimilar. And for example, here you see samples from Central and East Africa that are closer in geographical distance and also less or more genetically similar. This is an overview of previous studies that have been performed. It's not an exhaustive list on predicting geographical location, and it's been done for PF, PV, and also for other species. Results to now are, I think, very promising, but not all methods work as well as others. Then I'm going to show you some data of the PF7 data set. And I'm going to start with the genetic distances that were calculated with the 101 SNP barcode. And the calculations were done with GRC malaria. So on the x-axis, you see genetic distance. And these are genetic distance distributions of 3 groups. They were randomly chosen So the bottom one is a group that has sample pairs of which both samples came from Laos. So this is a within country group. And in the yellow distribution you see is a group that has one sample from Laos and the other sample pair came from Myanmar. And then the top one is a group that has one sample from Laos and the other sample from Kenya. So what you would expect is that the samples from the pairs that both came from Laos are more similar to each other than the pairs that have one from Laos and one from Kenya, which here you can see is the case, is the median of the Laos group is lower than the median of the Laos and Kenya pairs. And what you can also can see here is this little bump at 0, this genetic distance of 0, which indicates clonal expansion. And these are all averages, and what we would hope is that we could get more separation and more maybe more separation if you go to two different methods. We are currently in the GenRe-Mekong project. We are using the 101 SNP barcode, which it would be great if we could also use that for answering of the prediction use case for efficiency reasons. However, it's also possible to look at other genetic information. You could approach this in two ways. So one would be to add more genetic information, and we could add more SNPs up to approximately 100,000 variants from the whole genome. Or you could choose, like Sarah Arben touched upon, you could increase the informativeness of genetic information. So one option would be to select variants that are do specifically well for separating samples based on geographical location in your data set at hand. However, the risk then is that you would get overfitting, or that could be a risk. Another option would be to increase the informativeness of the segments you use by using, let's say, microhaplotypes, which have more alleles per more variants per segment. So here we see the same distribution on the top that you saw in the slide before. And in the bottom, you see the same groups, only then with genetic distances calculated with whole genome sequencing. And what I mean with that is that they were, the variants were chosen which included all typable SNPs with a minor allele frequency of at least. Bye, Dr. Sid. Thank you. See you next time. And which resulted in 41,000 SNPs included in the calculation of these genetic distances. And what you can see is that the separation between the groups becomes larger, which is what we would hope to see. And the bump of clonal expansion remains. And now, first, a little bit about the levels of difficulty, potential levels of difficulty when looking at importation. So the most easy scenario would be when you have importation from a different continent, let's say from a migrant worker, and then it will be very clear when you look at the genotype that it's not from your population, your local population. But when there is potential population from a neighboring country, which I can imagine that those are the most frequent things that occur with cross-border travel, then it could be either a challenge. For example, let's say that there is you see a strain that has previously only been detected in Laos, while you detect it now in Vietnam, and then you could potentially label that as importation. but we also know that there has been spread from certain clonal strains, resistant strains in the GMS, and with that it could potentially be very difficult. Although, as Varanya just showed in her presentation, the epidemiological situation in the GMS has been changing. So I'm not, maybe going forward it wouldn't be that big of the proportion of samples that we see in the GMS. So this is a very simple approach in which we are looking at, again, I took the samples from Laos and then the most genetically close sample pair in the dataset of PF, the malaria gen PF7 release. So these are almost 1,000 samples, and the mean genetic distance was a 0.06. So it doesn't say a lot, but it's close to each other. And then when you look at the distribution of the sample pairs, of which it was the closest sample to 5 more minutes, then you see that 74% had a sample pair made in Laos, and then the top 3 were all GMS. These genetic distances, by the way, are calculated using the 101 SNP barcode. And then you can also see from 5 to 10, the spot 5 to 10, these are small numbers, and the genetic distances are very high here. So I think these are non-informative results. So when using the 101 SNP barcode, maybe above a certain genetic distance, the country of origin of your pair mate is no longer informative. We could have a look at if it would be possible to set such a threshold. And also there might be a challenge if the data set does not contain samples that are more genetically similar. However, when we're looking at the same data set, but then with genetic distances calculated based on whole genome sequencing, we see that for the same samples, all of these were, the closest pair was either in Laos, 90%. So that's really, I think, really reassuring. And then the second and third Vietnam and Cambodia. So in this case, all of the Laos samples had a close pair in the Eastern GMS. Discussion and future work. So, of course, what I showed, linking it to the most close sample, is just to get an idea of the data, but we want to use look at several approaches going forward. So, for example, here you have an orange sample, and you want to know based on genetic data from which country it most likely originates. Then here you see a cluster of samples that are also orange, and they came from Laos. So you might classify the samples being from Laos. You can also use ranking, and then you would line up the samples based on genetic distance, and then make an educated, not guess, but decide what is where the sample most likely came from. And of course, there's also the factor of time. So let's say you have a group of samples, and they are all equally genetically similar to your sample of interest. Then, for example, with a clonal strain, then you could also have a look at the time. And if the older samples were all from, let's say, Thailand, and the newer all from Laos, then you might be inclined to think this sample came from Laos. So concluding, genetic information has the potential to reveal geographic location, and it's potentially useful in addition to travel history, which is currently used. It is important to have representative data sets for each region that you're interested in. And then our planned research. So we will look at several ways to use genetic information. So the 101 SNP barcode will be our starting point, but we also have a look at, for example, microhaplotypes and whole genome sequence-wide SNPs. We want to find the ideal balance between resolution and practical efficiency, and then to several methods we want to consider. So I showed clustering, ranking, adding time as a variable, but potentially also machine learning. And then, yeah, we can consider different formats of geographical location prediction. So start off with country, but can also go to province or coordinates, depending on what is most practical in use for the use case. And then lastly, there are cross-border resistant clones that maybe need to classify as cross-border. So previous studies that have looked at this had difficulties separating GMS samples. However, as I said, the current epidemiology in Eastern GMS has shifted to more diversity, so that might help us a bit. Yeah. I would like to thank all the participants in the GenRe-Mekong study and all the collaborators and the funders as well. Thank you.
Very much, Tess. Yeah, so this is very much work in progress, and I think over the next few months we will be testing different strategies, different mechanisms, and hopefully home in on a combination of things that give us good traction. Any questions from yeah, Richard?
Hi. It was just thought. So we've been thinking about this for a while with the Broad and others, and it's difficult, as you know. But maybe using a different geographic phenotype might help to separate better. So I showed a bit about where they live, but sometimes that's quite far away from the health facility. So instead of that, it might help to improve the separation. But also sometimes they live in a different country, but that's not necessarily captured. And then a step on from that is if there's really good quality travel data, maybe that's a good way to also cross-validate and help separate. I don't know how far we'll get, but it's worth a try.
Yeah, I definitely think that's that's a very good point. As I say, we will have to consider a lot of different dimensions to this and different data points. Yeah. Yeah, Liz.
Do you think you could use a phylogenetic approach? So kind of build a tree of everything and then find the nearest neighbor on the tree?
Yeah, so we've built a phylogenetic tree with the 101 SNP barcode, and then you do see separation based on continent, but I think after that it becomes a little bit fussy, but yeah, unclear. So maybe with the whole genome wide SNPs, you could get a clearer tree, but yeah, could try that. What do you think, Oliver?
No, sadly, even the whole genome sequence data, I mean, in the Greater Mekong subregion, it's quite informative. If you go to West Africa, for instance, it just doesn't work. And I mean, you can't separate neighboring countries in such a easy way. It's because of recombination. It's very different from viruses and so on. So the techniques that work for COVID just don't work for malaria. That's just a fact of life. You have to think differently. I suspect instead things like microhaplotypes and so on, the type of techniques that Sarah showed earlier on, may actually be more helpful in the long run, even with falciparum. Sorry. Yes, Liz, the other Liz.
Just want to ask you, yeah, more on that point, Oliver, because surely this becomes most critical when countries have almost eliminated. And so it's not so many cases that they're worried about importation. And when you get to that point in Africa when you want to do it again, hopefully transmission would be lower. So won't whole genome have the answer in the end in a low transmission kind of scenario?
Can I
You
take
might,
it?
yeah,
Okay.
you can answer.
Yeah, I think so. And also, I mean, the nice thing about that is that you can do a sort of tiered approach where, yes, you look at the 101 SNP barcode, and then if it looks like it might be imported, then you go to whole genome sequencing, and you can look in more depth. I think that's the case. But in the Greater Mekong subregion, what we've seen is that there have been sort of large clonal expansions, and they really complicate things because, hey, it's a clonal expansion, so they're identical either side of the border, basically. But maybe really as we get closer and closer, you will get more differentiation just simply because they're more isolated. So I think we have to watch the situation as it evolves and decide on the best methods. But definitely at that stage is when you get all your biggest guns out. Yeah.